Hello, my name is Jason Chanko. I'm an applications engineer for Rigol Technologies. I'm here to introduce the DSA815 series of spectrum analyzers from Rigol. Let's start out by going over a little bit about what spectrum analyzers are capable of, or what are they used for. Much like an oscilloscope, the spectrum analyzer is going to show amplitude, but instead of showing amplitude with respect to time as in an oscilloscope, it's actually going to show it with respect to frequency. And so what we can get is a very good indication of a frequency level and its amplitude relative to absolute value, but also relative to one another. Some typical applications are monitoring RF or radio communication channels. How much bandwidth a particular channel may be taking up is a pretty common example. Measuring filters if you're designing radios or you're using filters to help to clean up some of your signal levels. You can then characterize the filter with respect to frequency using a spectrum analyzer and a tracking generator, which we'll get into a little bit later. Also, another application is EMI and EMC pre-compliance. If you're doing any kind of board design or any kind of electronics, you're going to have that board, or they're going to have that end product qualified based on the area that you're going to be selling into. And for an example, if you're going to be selling into the United States, you're going to have FCC compliance. And so having a spectrum analyzer on hand can allow you to do some troubleshooting ahead of getting that certification. And then also RF education. If you want to show some things, Fourier analysis, for example, you can very easily show some of the frequency domain using a spectrum analyzer, which can be very helpful. So if we do a quick run through of the buttons and the display that we have here, again on the left-hand side we're indicating our amplitude, and then on the bottom we actually have frequency. So we're going from a start frequency to a stop frequency, and it's scanning across that periodically. On the left-hand side, we also have status of various settings that we have, the capability of changing. We have a help key, we have a print key, and a preset. Preset gets us back to whatever conditions we program that preset key for. It can be very helpful. In this case, I have it set to factory defaults, so by pressing it, I go back to factory defaults. The print key, if we are to put a USB memory stick into the front panel, we can configure the print key to print a bitmap image of the full display as well as the menus and settings directly to that USB drive, which can be extremely helpful. Alright, now we'll take a look at the frequency key, or frequency menu. We have center frequency, so we can select the center frequency value, and then it's going to adjust the span accordingly. So if we set our center frequency, in this case is 750 megahertz, our start frequency is 0, so we're going from 0 to stop frequency of 1.5 gigs. So we're doing a full span of the frequency ranges that are capable of being scanned on this particular instrument. Again, this is a 1.5 gig max, so we're going from 9K to 1.5 gig for each scan. So down on the bottom here, we're showing, here we're indicating our center frequency, 750 megahertz, resolution bandwidth. Resolution bandwidth is the size of the detector opening that is then being scanned. The wider that resolution bandwidth, the more spectral content we're taking per frequency step as we're scanning through. So we have less resolution, but it scans more quickly. By shrinking that resolution bandwidth, we get a much higher degree of resolution, but each scan then takes longer. It's sort of the catch-22, I guess, of the spectrum analyzer. Let's go back through signal tracking. If we have a peak, it will actually allow that whole span to follow that peak as it's scanning along. So you can imagine if we have an FM signal and the FM signal is moving, signal track would follow that FM signal back and forth. Peak to center, if we have a peak and it's off axis, we can then press peak to center and it will pull the entire wave, or it will pull the entire display to show that peak in the center. So instead of being 750 megahertz as an example, if we had a 1 gig peak, it would pull the 1 gig peak to the center of the display. Now we can go on to span. Span, again, is the frequency range that we're scanning across. In this case, we're doing a full scan, or a full span of 150 gigahertz. I'm sorry, 1.5 gig. If we wanted to change that, we could go to 100 and press megahertz, or we could go back to 1.5 and press gig. Again, we do this particular instrument, we have the ability to just enter directly in units, which is really nice. because instead of having to put 1.5 and a whole lot of zeros afterwards, or 1.5 and a whole lot of zeros to get gigahertz, we can just select units. Or we can use the scroll wheel if we just want to change a few values or change them in smaller increments. Again, we can always get back to full span by pressing that key. But then there's also zero span. Zero span mode works very much like an oscilloscope. It actually takes the center frequency that we've selected. In this case, we're running, again, center frequency is going to be 750 megahertz. If we go back to span and we press zero span, at that center frequency, we're now going to be basically, we are analyzing signals that are only at 750 megahertz. And now this is with amplitude with respect to time. So you can actually look at time varying signals or the actual modulation of the signal at that particular frequency level. So you can think about it as a limited bandwidth, extremely limited bandwidth oscilloscope. Now you can use that if you have a particular code or something like that that's being sent at a particular frequency level or value. You can watch the actual bits, let's say, of that signal coming through, which can be helpful. We can also go back out to full span, and we can zoom in and zoom out, and then we have a last span. So if you zoom in and you're not exactly happy with the area you've zoomed into, you can hit last span, and it will pop back out, which can be extremely helpful as well. Now let's take a look at the amplitude menu. So under the amplitude menu, we've got auto scale, which is going to adjust the actual scale, the values of each of the divisions to match the incoming input. We have reference level. Again, reference level is that top line. So if we wanted to go to 10 dBm, again, we could press 10 on the keypad and press minus dBm, and now you'll note that it says reference level minus 10 dBm. So basically move that whole window up. Let's go back to 0. And then input attenuator. So the DSA815 has an input attenuator that automatically, or as in factory defaults, automatically comes up as 10 dB. The idea is that we're going to attenuate that input just slightly, and it helps to protect the sensitive circuitry just in case you have any transients that may be discharged while you're connecting, or if you have a source that's connected that you're not entirely sure what that value is going to be. A good idea is to put in a level of attenuation in order to be able to protect that front end. Generally leave that on auto. Scale per division. Again, we have 10 dB per division in this particular case, but we can change that very easily. You can also change that amplitude scale from log to linear. And units, this is an area that we get a number of questions about. You can set the units into dBm, dB microvolts, dBmV, dB microvolts, dB volts, and volts and watts. We can also set a reference offset. You note down here it says 1/2. That means we're on menu page 1 of 2, so we can down arrow to get back to the second page. And now we have auto range, which is going to select the right range value for the amplitude of the signal that we have. Also standard with the DSA815 is an RF preamplifier, so we can enable that, and you'll note that the noise floor then drops. I think it's a 10 dB RF preamplifier. We also have correction factors. Correction factors, and I'm just going to enable those, allow us to, let's say we have an antenna that has gain or loss at a particular, in a particular frequency range. We can then select antenna and we can edit and enter those frequency values and their amplitudes so that you can auto-correct for any changes for the cabling or antenna or any other elements that you may have that you're testing. You can add those or subtract those values directly on the display by using the correction values, which can be extremely helpful as well. I'm just going to get back out here. We'll get back to amplitude, and we're on page 2. Then we also have input 50 ohm and input 75 ohm. That's strictly mathematical. It is not, it is a 50 ohm input on the hardware, and so we want to, if we change the input impedance to 75 ohm, you want to make sure you're using a 50 ohm to 75 ohm to 50 ohm adapter to that particular input in order to be sure that you're going to physically have that connection. Again, this is just mathematical, so that the actual values that are shown are corresponding to a 75 ohm input instead of the standard 50 ohm expected with the spectrum analyzer. Now let's take a look at the bandwidth and detector settings for the 815. Press the BWDT button, and you can see we have the resolution bandwidth settings. The minimum resolution bandwidth for the DSA815 is 100 Hertz. We also have video bandwidth settings, V to R ratio that can be set. Detector type, let's take a quick look through those. Standard detectors are positive peak, negative peak, sample, normal, RMS average, and voltage average. As an option, we do have an EMI toolkit that allows you to have a quasi-peak measurement. Again, that's used typically for EMI and EMC testing. Let's take a step back out. And now let's take a look at the sweep and trigger. So we can see that we can set the sweep time. Typically that sweep time is going to be on auto, and it's going to be based on the amplitude and based on the sweep configuration that we have set. The frequency range and the span and the resolution bandwidth are going to determine that sweep time if we're in auto mode, and that's going to be calibrated. If we go to a manual mode, that's going to be uncalibrated because we're actually forcing the box to do things that it's not necessarily optimized to do in a calibrated sense. We have auto sweep time. We want to keep that normal, or we can go to accuracy mode, and then mode we can go continuous or we can go single, and single we can just press single trigger if we wanted to do that, if we wanted to just capture one image. We also have the ability to do an internal trigger, which is going to be free run, but we can also do external. There is a BNC connector on the back, a TTL level signal, so if you wanted to trigger it in an automated way in order to capture images, you could do that as well. You can set the number of scans per trigger using that key there, the numbers key. Then let's move on to our trace. The trace, we have 3 traces that are selectable. In this case, we're doing trace 1. You can select trace 2 or trace 3. Trace 1, and then we have trace type. So we can do max hold, min hold, video average, power average, freeze, and then you can also have a blank screen. We have a number of averages per trace. Is user selectable. We can also do trace mathematics if you wanted to add one channel or one trace to another trace, or perform basic math on those. You can do that and multiply by constants. We have clear all, which is going to clear the screen. There's also a pass-fail area. Pass-fail is useful for a number of tests. Okay, so I'm just going to enable pass-fail, and you can see that when we enable pass-fail, we actually have criteria down on the bottom. We can set up pass-fail. With the DSA815, we have 2 limits that are enabled. One, we can enable upper, or we can enable lower. Again, upper, we cannot exceed upper, or it will be a failure. Lower, we cannot exceed lower, or it will be a failure. So they are more like a window, upper and lower, around a certain value. You can use this to edit and actually build around a particular channel. Let's say we were doing frequency modulation. We could build a window around the frequency modulation. If that frequency went outside of the upper limit, it would be a fail. Or we could also use the limit line, upper limit lines especially, for EMI and EMC compliance. We can have a dB value that cannot be exceeded at a particular frequency range, and if we were to pass over that value, we would have a failure. We could set the x-axis as frequency or time. We can do frequency interpretation, log or linear. We can do relative, pass or fail we can stop on. Let's go to page 2, and we can delete our limits, and we could also turn a beeper on if we wanted to have an automated test. So that can be very helpful in an automated test environment.